Okay, so welcome to this course of cryptography and network security. So I shall be in today's class I shall be introducing this topic, and I shall be trying to address about certain issues which are important in crypto and network security. So this course essentially deals with the communication of data between between a sender and a receiver, and the idea is that the sender and the receiver are communicating information over an insecure channel, and there is an eavesdropper who is trying to essentially understand what information is being transferred from the sender to the receiver. So the objective of the sender and the receiver would be to use cryptography or principles of cryptography, and to ensure that certain properties of the data are not compromised. So for example, the integrity of the data, that is whether the data has been modified or not, the secrecy of the data, that is what information has been transferred, and there are similar certain other objectives which needs to be satisfied. So essentially cryptography or the principles of cryptography gives you certain mechanisms or certain principles of how you can carry these operations forward, how you can satisfy these properties when you transfer data, transfer information over an insecure channel. So that is the objective of essentially studying this subject of cryptography and network security. So in order to understand that, we will see a communication game, and we will see how essentially what are the issues which are involved in such a particular such a game. So then we shall define the concept of protocols as opposed to something which we know as algorithms, and then we shall define some magic function which will be used to solve the simple protocol or simple game that we consider. So this magic function is something which we will try to understand, and essentially throughout the course of throughout this entire course we shall be studying various techniques, various methods how you can realize this magic function. So these magic functions are realized in the form of cryptographic functions. So in today's class we shall end with this particular note. So going into the communication game, let us consider a game where Alice and Bob, who are essentially, you will be seeing in the literature this Alice and Bob, you can imagine that they are the most famous persons in cryptography, that is they are the most widely popularly known names for the sender and the receiver. So Alice and Bob are the two most famous persons in cryptography, and they are used everywhere. So Alice and Bob essentially are just two names to denote the sender and the receiver. So we can understand, like we can take Alice to be the sender and Bob to be the receiver of information. And just let us consider a scenario where Alice and Bob wishes to go for a dinner together, and they want to and Alice would like to go for a Chinese food, whereas Bob intends to go for an Indian food. So the question is that if Alice and Bob wants to dine together, then how do they resolve this problem of not concurring at what they want to go for, what they want to have for dinner? So how do they resolve this problem? Very simple. They can use an unbiased coin. So this can be one example. That is, if I believe that both of them are not ready to compromise and they have got very strong desires either to go for Chinese food or an Indian food, then what Alice will do is that Alice will toss an unbiased coin. So that by the term unbiased coin, we mean that the probability of the coin, when we toss the coin, the probability that the outcome is a head is half, and is equal to the probability that the outcome is a tail. So so Alice, what she does is that she tosses a coin with her hands covering the coin, and asks Bob of his choice. So essentially Bob has to say that head or tail, and if Bob's choice matches with the outcome of the toss, then they go for an Indian food, that is Bob wins the game. Else Alice has in her way, which means Alice says that okay, we have to go for the Chinese food. So this is a very quite an acceptable solution, assuming that the coin is an unbiased coin and the coin has got only two possibilities, that is it can either result in a head or it can either result in a tail. So considering this situation, this is quite an easy problem which can be solved. But imagine, that is what happens in real life is that most of us are quite distant apart. That is, for example, imagine that Alice and Bob are two friends who stay a far distance apart, and for them they want to meet at one place and have the dinner, but where do they meet? That's the problem. So therefore they cannot have an unbiased coin, and they cannot toss that at the same place. So consider the situation when both of them are far apart and communicate through a telephone. And so therefore so what is the essential difference of when we are separating out Alice and Bob over a large distance from this particular problem? So what is the essential problem? So the problem is essentially of something which we call trust. That is, when Alice and Bob are quite a distance apart, then if, for example, if Alice tosses the coin, so imagine that they engage the same technique, that is, both of them say that, both of them use the unbiased coin, and even when they are distant apart, then Bob cannot see the outcome of the toss. So therefore when Alice takes a coin and tosses, since Bob is at a distance apart, Bob is unable to see the outcome of what happens at Alice's end. So therefore Bob does not trust Alice, so Alice can play malice. That's the point. Similarly, so therefore they have to do something better. Okay, so they have to do something different. So in order to do that, so what they do is that, so therefore the problem is that in this case of trust, and Bob cannot trust Alice, as Alice can tell a lie. So the question is now, how do we solve this problem? So these kind of problems are very popular in our network security domain, and often involve not only two parties but actually a multi-party scenario. So therefore there are more than one party who are playing this game. So these type of scenarios are very commonly or technically known as protocols. So therefore in order to resolve the problem, both Alice and Bob has to engage in a protocol, and they have to solve this problem. So therefore they have to engage in a protocol, and so therefore protocol is something which is similar to an algorithm, but in algorithm, so it's basically a sequence of steps in order to solve a problem. But the thing is that in case of protocols, we have got more than one people who are, or more than one parties who are involved in a game. So that's the idea. So in this case we have got two parties, like we have got Alice and Bob, who wants to solve the problem, and they need to concur upon an agreement, but they are not at the same place geographically. So in order to do that, they use a magic function, and I call that as fx, or denote that as fx. Okay, so let us see what these properties of this magic function should satisfy, so that this problem of trust can essentially be resolved. Okay, so let us consider some properties of the function fx. Okay, so you assume that the domain and the range of fx are the set of integers. So therefore you understand what is meant by domain and range. So imagine that x is chosen from a pool of values, and I call that to be the domain of fx, and all the possible values that fx can result to is called the range of fx. Okay, so therefore imagine that x is chosen from the set of integers, and it also results in the set of integers. Okay, so therefore fx has got a domain and range, both of which are the set of integers. Okay, so for every integer x, it is easy. So therefore the property of fx are as follows. So the property of fx, the first property is something which we call as one-wayness. Okay, so one-wayness means very simply that this function fx is easy to compute. Okay, so let's not go into what is meant by easy and what is meant by not easy or hard. Let's just take it as two terms. Okay, so let's not go into the technical details right now. So therefore what I'm trying to say is that for every integer x, it is easy to compute fx from x, but so therefore it's easy in one way, but given fx, it is hard to compute x. So therefore the problem is as follows, like if you take x, okay, so therefore the property of this function f is something which is called as one-wayness. Okay, so if I give you x, then to compute fx is easy. Okay, so therefore for example you can just take that, okay,
I mean, so you can just take x and very easily compute the value of fx. But if I give you the value of fx and I ask you what is the value of x, then this should be a relatively difficult problem. Okay, so that is what is meant by the one-wayness property of f. And actually, in literature, we will see that in spite of lot of research, we have got few candidates for one-way functions, but there are no concrete proofs which says that whether the function can be proved to be a one-way function or not. Okay, but this is the notion. So the notion is what? The notion is of something which I called as one-wayness, which means a function which is easy to compute but hard to invert. Okay, so I give an example which is believed to be correct. Like you take two prime numbers or two large prime numbers P and Q. So if I tell you that N is equal to P into Q, then given P and Q, computing N is a easy problem. It's quite relatively an easy problem. So if I give you P and if I give you Q, from there computing the value of N is an easy problem. But if I give you N and I ask you what is the value of P and Q, is believed to be a hard problem. So if I give you N and I ask you what are the corresponding values of P and Q, it is believed to be a relatively hard problem. So this problem is commonly known as the factorization problem. Okay, so this is a probable candidate for a one-way function. Okay, so this is one property which the function f needs to satisfy, and the other property is that it is difficult. So when I say impossible, I mean to say it's difficult to find a pair of distinct integers x and y such that fx and fy are the same. So this is also sometimes called collision resistance. Okay, so therefore if I give you a function f and I tell you that okay, now report to me two values of x and y which are not the same but which results in the same values of fx and fy, then this should be a relatively hard problem. So therefore it says that collision resistance means this, that is, so the next property is of collision resistance. Okay, which says that if I give you a function or given a function f, given a function fx, okay, output two values x not equal to y such that fx and fy are same. Okay, so this should be a difficult problem. Okay, I'll come to at the end of the class to explain a little bit about what I mean by an easy problem and what I mean by a hard or a difficult problem. Okay, so this is a hard or a difficult problem. Okay, so therefore it's not easy to give you to report two values x and y which will essentially result in the same values of fx and which will result in the same values of the output of f. Okay, so therefore if I take a function f, to take or report two values of x and y which are different but which results in the same values of fx and fy should be hard or impossible. Okay, so therefore this is the property f essentially satisfies these two properties. The first property is of one-wayness and the second property is of collision resistance. Okay, so let us assume that the magic function f essentially satisfies these two properties. So now let's see if Alice and Bob engages such a magic function, then does their problem of resolution get solved? Okay, so for the magic function f satisfies these properties of 1 and 2, and now the question is that if it does so, then does the problem of resolution get solved? So therefore, in order to solve this problem, Alice and Bob essentially has to engage the function f in something which I called as a protocol. Okay, so let's see what could be the protocol. So the protocol, both of them agree on the function fx. So therefore, they decide upon a function fx, and which they believe should satisfy these two properties of one-wayness and collision resistance, and they believe that, okay, and they assume that head will be represented by an even number x, and tail, or the outcome of tail, will be represented by an odd number of x. So see, I mean, what Alice and Bob are trying to do, essentially Alice and Bob are trying to do the same thing like tossing an unbiased coin when both of them were together. But now, since they are apart from each other, they cannot really do it straight away. So what they do is that they use this magic function f and essentially try to, which satisfies these two properties, and tries to do the same thing. Okay, so essentially they have to decide whether a head is resulting, I mean, so what they will do is that they will try to replace the function, they will try to replace the function f by, they will try to replace the unbiased coin by the function f, and we'll try to see that whether a head results or whether a tail results by the computation of the function fx. Okay, so what Alice and Bob does is as follows. So Alice and Bob essentially does the same thing, that is, now they need to do the coin toss by using the function f. So they need to do the coin toss by using the function f, and in order to do that, so therefore there are two possibilities, right? The possibilities are whether so what they are essentially trying to do here is that Alice chooses randomly a value x, so this x, if it is randomly chosen from the set of integers, the probability that x is even is the same as the probability that x is odd, and that is equal to half. Okay, but till this part there is no problem, but the problem happens, or the problem of trust happens, when Alice communicates this information, that is whether x is even or odd, to Bob. So here Bob, so we try to understand the problem. The problem is as follows, that is, if Bob predicts that x is even, or so therefore imagine that Alice essentially does a coin toss at its end, and depending upon the coin toss, that is whether the toss results in a head or a tail, it chooses the value of x to be even or odd. So therefore, if this coin toss results in a head, Alice chooses x is even, but if this coin toss is a tail, then x is odd. Okay, so Bob, so remember what was the game? The game was that Bob initially had to guess what was the parity of x, that is whether the value of x was even or odd. But the point is that since they are doing over a communication channel, what Bob is, why Bob is not believing Alice or doesn't have trust on Alice is that, so after the result of the coin toss, Alice can essentially say or communicate a wrong information to Bob. That is, even if Bob is correct, like for example the coin toss at Alice's end was actually head, and when Bob Bob also had said that head would have been resulted, head would have been the outcome. So what Alice can do is that Alice can pass on a wrong information that the result was a tail. So in order to prevent such a scenario, Alice and Bob shall be using the function f. So in order to solve this problem of trust, Alice and Bob shall be using the function f to communicate the parity of x, that is whether x is even or whether x is odd. That information now Alice will not pass just on the clear, but instead will compute the value of fx and will pass on that information to Bob. Okay. So I believe that even if this is not clear till now, it will be clear. I will try to make it more clear. Okay. So just at this point, at least try to understand that an head event or an head outcome is being represented by even number x, whereas a tail is being represented by an odd number x. Okay. So what Alice does is as follows. So therefore I call this as a coin flipping over the telephone. So essentially they are flipping the coin, I mean, as we are done when both Alice and Bob were together, but only in this case they have to do, I mean, not solve this problem over the telephone. Okay. So what Alice does is that Alice picks up randomly a large integer x. So therefore when I say randomly, it's just like based upon the outcome of a toss at which Alice does. Okay. So Alice takes an unbiased coin, and it doesn't really matter at Bob's end whether it's unbiased or biased, because Alice doesn't have an advantage right now for about that. So just imagine that Alice picks up randomly a large integer x and computes the value of fx. Okay. So Bob tells Alice his guess of whether x is odd or even. So what Bob does is that Bob predicts that whether Alice, so therefore Bob predicts that whether Alice, what was the guess of Alice. Okay. So therefore so in this case Alice picks up randomly a large integer x and computes the value of fx, and this value of fx is now passed to Bob. Okay. So Bob now has the value of fx, and Bob, based on the value of fx, or so Bob essentially has got the information of fx, but now what Bob need to do is that Bob need to tell Alice his guess of whether x is odd or even. Okay. So I'll come to the properties, but first of all just try to understand the protocol. Okay. So then Alice, what she does is that Alice then sends x to Bob, and Bob verifies by computing the value of fx. Okay. So here there are two important things to be noticed. The first important things to be noted is that Bob has got an information of fx, and when it is trying to guess, that is whether x is odd or even, so in order to see that Bob doesn't have an advantage of guessing, means what? Means that the function fx should not reveal any information about the oddity or the even parity of x, which means that fx should not reveal any information about x, and that property is satisfied by the one-way-ness guarantee of the magic function f. Okay. So I mean, how we will do it, we are not really bothered at this point. We are just trying to understand the properties. Okay. So Alice now, and the other important thing is that, I mean, considering the end of Alice, when Alice is computing the value of fx, okay, and sending this value of fx, why is Alice doing so? Okay, Alice is doing so because if Bob's guess is correct, then later on Alice should not be able to change the value of x, that is change the parity of x, such that the value of fx which she has previously committed will remain the same. Okay, and this property, I mean, so what does it mean? So x, so what Alice will try to do, if she wants to cheat, she will try to change x to x dash such that the parity of x and the parity of x dash are different, and what is the other property? The thing is that the value of fx and the value of fx dash will collide. Okay, so that is how Alice will try to cheat Bob, because then it can say that, okay, see, actually what you have guessed is wrong, because you have guessed x, but whereas the correct value is x dash, and you see that you can calculate the value of fx dash and it will be the same as that of fx. Okay, but this is also hindered, or this is also not this advantage, and Alice also does not have this advantage because of the collision resistance guarantee or collision resistance property of the magic function fx. Okay, so therefore that is the reason why we say that the magic function fx needs to have the one-wayness property and also the collision resistance property. Okay, I hope it's clear till this point. So therefore if I do a security analysis, so the question is, can Alice cheat? Okay, for that Alice needs to create a y which is not equal to x such that fx and fy are the same. Okay, so when I say that y is not equal to x, which means in this case the important information is the parity of y and the parity of x are different. Okay, and such that fx and fy are same, and this is believed to be hard. And the other important thing is that, can Bob guess better than a random guess? So Bob listens to fx. Okay, so this so can Bob guess better than a random guess means initially Bob, so if Bob has not been provided with the information of fx, what should be the probability of Bob guessing correct? It's half, right? So even if when the information of fx is provided to Bob, the probability should still remain half. Okay, so his probability of guess is half, so therefore it should be still like a random guess, which means that the value of fx does not leak any information about the value or parity of x. Okay, so that is also being so these two are being guaranteed by the properties of the magic function f. Okay, so we will consider a little bit more concrete example. So this is a similar scenario where Alice and Bob wish to resolve a dispute over the telephone. So we can encode the possibility of the dispute by a binary value. So for this they engage a protocol. So what we have just now seen. So Alice and Bob, essentially what both of them do is like this. So Alice picks up randomly an x which is a 200-bit number and computes a function of fx as follows. Okay, so it computes the value of some fx value which I will describe just now. So what Alice does is that so let us consider this this particular example little bit minutely. So what Alice does is Alice sends to Bob the outcome of a function fx. Okay, so it chooses x at random. It chooses x randomly, and x is a 200-bit number. Okay, so it's a 200-bit means to the 201 string values, 200 number of 01 values. Okay, so it chooses a 200-bit number, a 200-bit value, and computes the value of fx. Okay, and sends it to Bob. So computes fx and sends it to Bob. So what Bob does is that now Bob sends to Alice the guess. So Bob now guesses whether x was even or odd. Okay, and sends this information back to Alice. Okay, so now Alice, what it does is that Alice needs to, so Bob needs to verify, right? So therefore what Alice does is that Alice now sends x to Bob, so what will Bob do? Bob will verify. Bob verifies by computing fx and tallying with the previously received value. Okay, so this is the basic protocol, right? So we are trying to so therefore now what we need to do, what do we need to do? We need to think of such a function fx. Okay, so we have seen that if this fx function satisfies the collision resistance and the one-wayness, then this protocol should give a fair evaluation or do something which was similar to when Alice and Bob did simultaneous, right? When both of them were together and they just did a random coin tossing. Okay, so therefore both of them do not have any additional advantage in the game. Okay, so in order to do that, we will consider a concrete example of the function f. So just consider the following function. So imagine that f essentially is, so therefore you know that x has been chosen to be a 200-bit number, right? So I denote that as a 01 string of 200-bit values, and what f does is that it takes in the values of x. So therefore x is like something like from 0 to 199. So it takes the first 100-bit values and it takes the next 100-bit values, okay, and I call this part, so therefore it takes this part and does a bitwise OR between these values, okay. So therefore it does a bitwise OR, okay. So all these bits are getting ORed. So therefore this is ORed with this, and you get this, you get you OR this bit with this, and you get this. So this is nothing but the MSB part, okay. So therefore you just take the MSB part, bring it here, you take this part and do a bitwise OR between the bits, okay, and you get the resultant output, okay. So let us consider a simple example, like see, for example, if there is a string like 1 1 1 1 and so on, I mean there are 100 bits, 100 values here, and similarly the next 100 values are say 0 0 0 0 and say 1, okay. So what will be the corresponding, so this is x, okay. So what is the corresponding value of fx? It is 1 1 1 and so on, and you OR that with 1 0 0 and 1, okay. So therefore if you do a bitwise OR, you get a 1 here, and this is again a 0, so you have got a 1 here, and so you get a 1 for all the values, okay. So this is your corresponding value of fx, okay. So let us just imagine a function f which looks like this and try to compute the success probability of Alice and Bob, okay. So for example here in this function, so therefore this function can also be replaced by other possible candidates, okay. This is just a simple example. So for example we could have replaced this OR by an XOR, okay, and we could have computed the similar properties, but I'm trying to find out this particular, I mean just taking this as an example and try to compute what is the probability that Bob succeeds, and that is Bob is correct in his guess, and what is the probability that Alice can cheat, okay. So we are interested in these two probabilities, and what we have to see is that whether there is an additional advantage over a random coin toss, okay. So therefore in typically we will try to compare this with a random coin toss, and based upon that we will see that whether this function f is really a candidate for a magic function or not, okay. So how do we calculate these values? There is a probability of Bob will succeed or probability of Alice will cheat. So for that we have to observe the properties of this OR function, okay. So here is just what I have said to you. That is a more concrete example is this, that is if Bob's guess was right, Bob wins. So this was a game. If Bob's guess was right, Bob wins, otherwise Alice has the dispute solved in her own way, okay. So what they do is that they decide upon a function like this. So f is essentially a map from x to y, where x is a 200-bit random variable and y is a 100-bit random variable, okay. So the function is just as I have told you just now, that you take the most significant 100 bits of x and you OR that with the least significant 100 bits of x. So x is just a 200-bit string, and you OR, or you do a bitwise OR between the first 100 bits of x and the least 100 bits of x, okay. So here OR denotes a bitwise OR operation, okay. So what we are interested now in doing is that we are interested in calculating the success probability of Bob and the probability that Alice can cheat, okay. So in order to do that, we have to first of all think of an algorithm or a strategy for Bob, okay. So Bob essentially has to adapt a principle or adapt an algorithm or something which we call commonly as the experiment of Bob, okay. So what is Bob's objective? Bob has been provided the value of fx and Bob has to guess the parity of x, okay. So therefore Bob needs to do something good. So now see that this property, or rather if you see the property of this OR function, okay, you know that what is the, if I just do a simple truth table of this OR function, okay, so you know that if there are two inputs like A and B, and this is your A or B, okay, so if you just consider the binary truth table, so you see here that there is only one value which is 0 here, but the rest of the things it reports in a 1, okay. So therefore this property, or rather this observation, will essentially, I mean, Bob will exploit to make its guess more favorable, okay, or I mean to enhance its probability of success. So in order to do that, you see that Bob essentially has got the value of fx, okay. So Bob has got the value of fx, and what it will observe is that what is the least significant bit of fx, okay. So you see that if the, so there can be two possibilities here. It can either be 0 or it can either be 1, okay. So if it's a 0, what does it mean? So so just think of the function f, right. So just think of the function fx, okay. So fx means what? You have got, so therefore just if you just think of the first 100 bits here, so fx means what? You have, this is the first 100 bits, okay. So just consider that this is some value, and I call that to be the x0 value, okay. So it is the least significant bit of x, and there are other values here, so there are 100 more bits here, okay. So therefore how do I compute fx? I just take this and I OR with this, okay. And if the resultant value or the least significant bit of the result is a 0, which means that 0 is the OR of, so 0 is the OR of x0, and so you have got x0 to x99 here, and this is your x100 bit, okay. So therefore this is the OR of x0 and x100, okay. So if this value is 0, you see that in the truth table of A or B there is only one possibility, that is both A and both B are OR. So therefore you can say with a probability of 1 that x0 is 0. So what does it mean? It means that x was an even value, okay. So therefore immediately the parity of x gets ascertained, okay. So therefore if this be so, then Bob has got, I mean with a probability of 1, Bob can say, Bob says x is even, okay. Otherwise Bob says x is odd. So you see that this particular case, in this particular case, Bob has a probability of success of 1, but in this case the success probability of Bob is not exactly 1, okay, but it's slightly different. So can you say what is the probability here? So you see that if this be 1, okay, so if this be 1, so what are the possible cases? It can be either, so therefore it means that it belongs to this case, right. So therefore it means that 1 is equal to x0 or x100, okay, and we are interested in the value of x0. You see that how many values can, I mean how many possible cases you can, I mean in how many possible ways you can get a 1 here. It could be either be a 0 1, it could either be a 1 0, or it could either be a 1 1, okay. So you see that in these three cases there are two cases for which this x0 value was actually 1, which means that x was odd, okay, and that is what Bob is saying. But in the other case, and there is one case out of these three cases where Bob will fail. So therefore the probability of success here is actually 2 by 3, because in two cases Bob is correct out of three cases, okay. So here in this case the probability of success is 1, but here it's 2 by 3, okay. So Bob essentially can use this particular observation to develop a strategy, okay. So the strategy therefore is very simple. The strategy is like this, that is, if the 0th bit of fx is 0, then x is even, otherwise x is odd. So this is a simple algorithm or simple strategy which Bob can adopt, okay. So in this case the probability of success of Bob will be 1, but in this case the probability of success of Bob will be 2 by 3, okay. But you note one thing, that is x was randomly chosen, okay, but the value of fx is actually not randomly chosen. Okay, so therefore if I say you what is Bob's probability of success, you cannot straight away assume that the value of fx 0 being equal to 0 is half, okay, and compute the value of fx. You have to do slightly different thing, that is what I will come to next. Okay, so therefore, but this is correct, that is the probability that x is, if it says that x is even, so in this case the probability of success of Bob is 1, but in this case the probability of success of Bob is 2 by 3 as we have just worked out. Okay. So next we are interested in calculating what is Bob's probability of success. Okay. So how do we calculate Bob's probability of success? Okay, so you note that there are two possible ways, that is x, since x is randomly chosen, x can either be even or x can either be odd. Okay, and therefore the probability that x is even is equal to the probability that x is odd, and that is equal to half. Okay, so now the probability that Bob succeeds can easily be found out or can be written in this fashion. Okay, so therefore there are I mean, if I want to calculate this this particular probability that Bob will succeed, there can be I can do this in this fashion. So probability of Bob succeeds, okay, is equal to probability that x is even multiplied by probability that Bob succeeds, conditional probability. So it's a conditional probability, and here the condition is that x is even. Okay, and basically what I am trying to do is that I am trying to split the case, split the possibilities into two mutually exclusive cases. Okay, one is when x is even, and the other one is when probability of when x is odd. Okay, so therefore I write the other part as probability of x is odd multiplied by the probability that Bob will succeed given x is odd. Okay, so we split this into two mutually exclusive cases, and what is the probability that x is even? I know that that is half, and I also know that the probability that x is odd is also half, so I can take this half common, and I have got probability that Bob succeeds given x is even, okay, plus the probability that Bob succeeds given that x is odd. Okay, so now you see that we have got two cases. Okay, so one is that when x is even. Okay, so when x is even, then that means that so therefore, so what is the probability that Bob will succeed when x is even? Okay, so x is even means what? X is even means x0 is 0. Okay, so what is the corresponding value of fx0? It is x100 or with x0. Okay, so in this case it is equal to x of 100. Okay, so depending upon the value of x100, Bob will say it to be 0 or 1. Okay, so Bob will predict its value. Okay, so you see that if x of 100 is also 0, okay, so in that case the result is 0, and therefore what Bob guesses is correct, that is Bob guesses x to be even, and that is correct. Okay, but if x100 is 1, then this result is 1, so therefore Bob will see this 1, and using its strategy Bob will guess that x is odd, but actually x is in this case is even, so therefore Bob fails. Okay, so therefore when x100 is 0, then Bob is successful, but when x100 is 1, then Bob fails. Okay, and what is the probability that x100 is 0 or 1? It's half, because x is randomly chosen, therefore all the bits being, any of the bits being equal to 0 or 1 is actually equal to half. Okay, so therefore this particular value, that is Bob probability that Bob succeeds when x is even, is actually equal to half. What about this case when x is odd? So x is odd means x of 0 is 1. Okay, and therefore x of this value is equal to x of 100 or with 1, and this is always 1. Okay, so therefore seeing this 1, Bob using its strategy will always guess that x of 0 is 1, and therefore its probability of success is actually equal to 1 when x is odd. Okay, so now we combine these two things and we obtain what we have written out in this slide. So we obtain that we write half into half, that is plus half into 1, and therefore we get a probability of that that Bob is successful is equal to 3/4. Okay, so what should have been the ideal probability of Bob succeeding? It would have been half. Okay, so therefore we see that there is a significant excess over half. Okay, then that excess is 1/4, and that means that the magic function f which we have instantiated by this OR function is not correct. Okay, so therefore this is not a very good candidate for such a function. Okay, but this is an example. So let's see that we are just seeing that example in order to appreciate the problem. Okay, and motivate the study of this present course. Okay, that is why at all we are studying cryptography. What is the purpose? That's why we are trying to see some. We are just seeing a possible a simple game, and we are trying to see a possible candidate of the function f. Okay, but you just try to understand first that this particular function f which we have chosen is not actually an ideal candidate, because here in this case the probability that Bob succeeds is not actually equal to half, but is quite greater than half. Okay, so it's significantly larger than half. Okay, and therefore we are not actually, I mean, Alice and Bob are not, should not be satisfied with the function f. Okay, and what is the probability that Alice will cheat? That is Alice's cheating probability. So you see that in this case, remember that we will compute Alice's cheating probability irrespective of Bob's strategy. So therefore Alice really does not know what strategy Bob has taken, so Alice still wants to cheat. Okay, so therefore in order to cheat, what does Alice need to do? So you see that Alice has committed the value of fx. Okay, and therefore based upon, so therefore when Bob guesses, that is what is the parity of x, that is which I mean what, in order to cheat, what Alice will do is that Alice will change the value of x or change the parity of x, keeping the value of fx intact. Okay, so therefore Alice can cheat by changing the parity of x. Okay, so therefore Alice needs to change the parity of x such that here there should be an additional certain few words, that is the value of fx should be intact, the value of fx should not change. Okay, so in order to see, I mean, or compute the probability, let us divide this again into two cases like what we have done in the previous case. Let us divide this. The first case is x is even. Okay, so when so when x is even, okay, so therefore x0 is 0. So what is the value of fx? So there can be two possible cases, fx0 equal to 0 and fx1. Okay, this should be actually 0. Okay, so therefore the fx0 can either be 0 or it can either be equal to 1. Okay, so there can be two possible cases here also, that is if you see the case 1, x is even. Okay, so if x is even, the value of fx0 is again equal to x0 or with x of 100. Okay, so what is the value of fx0 here? It is equal to 0 because x is even, so x of 0 is 0. Okay, so therefore what is the probability that so therefore this is actually equal to x of 100. So therefore depending upon the value of x 100, whether it's 0 or 1, fx0 is 0 or 1. Okay, so therefore the fx0 being equal to 0 or being equal to 1, both has got a probability of half. Okay, because that depends upon whether the 100 bit is, I mean x100 is 0 or 1. So therefore this also has a probability of half and this also has a probability of half. Okay, so note that in this case when fx0 is 0, okay, then Alice cannot cheat. Why? Because in order to cheat, Alice needs to make the value of x odd and still result or still see that the function fx results in a 0. Okay, which cannot be the case. That is, if x0 is changed from 0 to 1, so therefore in order to cheat in this particular case, if I call this as a case A and I call this as a case B, so in this case 1A, okay, Alice cannot cheat. Why? Now because in order to cheat, Alice needs to do what? It needs to change the value of x0 to 1, but this implies that fx0 computes to 1, so which means that this is not the same as the previous case. Okay, so therefore Alice, so therefore this is not the same as what was initially reported, that is initially fx0 was 0. Okay, so in this case, so therefore this is not equal to 0. So therefore, since this is not equal to 0, so Alice cannot essentially change the value of x0 to some other, I mean cannot change the parity of x, but still keep the same value of fx. Okay, so therefore in this case Alice is unable to cheat. But what about case 1b? Alice can cheat. Why? Because in this case fx0 is actually equal to 1. Okay, so when fx0 is equal to 1, then, and we know that in this case x is even, so even if Alice changes x0 to 1, okay, this value, I mean this particular fx0 value does not get affected. So therefore the fx value is fx0 is still 1, and this is the same as that in case, so this is the same as in case 1b. So therefore fx does not get changed, but the parity of x is changed. Okay, so therefore Alice, what she has done in this case 1b is that although x was even, can actually change this x even to an odd value by just flipping the last bit, but the value of fx0 which she has committed does not get changed. So therefore Bob does not have any other way to understand whether that Alice has done this malice. Okay, so therefore Alice is able to cheat. Okay, so therefore Alice is successful to cheat. So therefore what is the probability that Alice is able to cheat comes from this particular case. Okay, and what is the probability of this? It's half. Okay, so the probability of this is half, and the probability that x is even is also half, and therefore the resultant probability in this case is actually equal to 1/4. Okay, so what about the next case, that is case 2? So in case 2, x is odd. Okay, so in case 2 x is odd, and therefore fx0, what are the possible values of fx0? So if x is odd, it means that x of 0 is 1. Okay, so now in this case, can fx0 be equal to 0? That is not possible, because if I have odd with 1, I will definitely get a 1. So the only possibility is here in this case 1, and in this case also Alice can cheat by a similar logic as we have done for case 1b. Okay, so Alice can cheat similar to case 1b. Okay, so therefore in this case the probability that Alice is able to cheat is actually equal to half into 1, because there is the only outcome here, and therefore the total probability that Alice can cheat is actually probability that Alice cheats or Alice can cheat is actually equal to 1/4 plus half, and that is equal to 3/4. Okay, so you see that here also Alice has got a significant probability of being able to cheat. Okay, so therefore this function f, I conclude from here, this f as we have defined is not really a magic function. Okay, so which means what? Which means that we need to find out such values of f which are really possible candidates of magic function, and that is the objective of this course. That is, throughout this course we shall try or see various techniques or methods which will aim at discovering this kind of functions, and they will be referred with various names like one-way functions, pseudo-random generators, hash functions, symmetric and asymmetric ciphers, and so on. Okay, so I will just conclude. So that is the objective of this course, but I will conclude with this with just a few words on what I meant by easy and hard. Okay, so actually I will be talking about this in more details throughout the course, and it will be more clear as we proceed in the course. But I mean, just to understand what is meant by practical efficiency, a mathematical problem is efficient or efficiently solvable when the problem is solved in time and space which can be measured by a small degree polynomial in the size of the problem. Okay, so the problem that describes the resource cost for the user should be small. Okay, so therefore what I mean by this is that when I am saying an easy problem is that with respect to the input size of the problem, the cost of your time or the cost of your space in solving the problem can be expressible in a polynomial with a polynomial of its input size, and the degree of the polynomial should be small. Okay, so for example, if I have got an algorithm which solves in a linear time complexity, I say that it is, say it's something like ON. Okay, something which we defined as ON, which means it's linearly dependent upon the input size. Okay, so as opposed to that, if I take a quadratic problem, that is if some problem like the time and cost of some, or time and space of some problem is proportional to the square of its input size, then I say that to be a quadratic problem. So therefore the quadratic solution to the problem, and therefore the time and space of such a solution is obviously more than what we get to get by a linear time problem. Okay, linear time solution. So therefore the idea here is that a mathematical problem, I call that to be easy, or I call that to be an easily solvable, is when the problem which is solved in time and space can be measured by a small degree polynomial in the size of the problem. Okay, and therefore as opposed to that, when I call that some solution is, some problem is really a hard problem or a difficult problem, I mean to say that the best algorithm that I know to solve this problem has got a time or space complexity or space which is proportional, or which cannot be really expressible in a polynomial with respect to the input size, and the degree of that polynomial is small. Okay, so therefore for example, if I have got a solution which is, say, an exponential with respect to the input size, for example, if I have to do, for example, so suppose the input size is n, and if I have to do a 2 power of n of n such, or 2 power of n amount of storage is required to solve that problem, then I call that problem to be a relatively difficult problem or a hard problem. Okay, so that is the notion behind easy and a difficult. So we also have to keep our practical efficiency in mind. For example, a protocol with the number of rounds between the users, if it increases quadratically with the number of users, then I say that not to be efficient. Okay, but it may be the best possible way to do it, but the researchers throughout the world will try to make that protocol better and or more efficient. So what does it mean? Now I mean to say that I will try to increase, or rather reduce the number of users and make it more and more efficient. Okay, so therefore it should not increase quadratically. Maybe it will increase linearly. Okay, so therefore we wish to make protocols or algorithms which are not only secured, but at the same time they are also efficient. Okay, so therefore efficiency is also another thing which we will always keep in mind in developing cryptographic algorithms. Okay. So I conclude this talk with this part with the reference which I have followed. So I have followed the book of Wenbo Mao for this part. It's Modern Cryptography and Theory and Practice, and there is a low priced edition from Pearson Education. And in the next day's class we will take up the topic of we'll have an overview on modern cryptography. Okay, so we will see the various cryptographic algorithms which are rather many various objectives of modern day ciphers. Okay. So we conclude this course with that. Thank you.